All right, this has been a very long section. We cover a lot of really important stuff here, but this is going to be the last video. So I have 1, 2, 3 more examples that we're going to cover. The first one, a guitar retailer sells electric guitars at a price of P of X equals negative 4.5X plus $1,500 when X guitars are sold. Find the instantaneous rate of change in revenue when 30 guitars are sold, and then interpret your answer. So this is similar to the last problem. We're selling, an item, guitars in this case, and we want a rate of change, but this time our rate of change is in revenue, not profit. It was profit in the previous example. So we need a revenue function. We know that the revenue function is equal to X times my price function. And we have that price function here. It's X times negative 4.5X plus 1,500. Okay. I'm going to distribute that X in negative 4.5X squared plus 1,500X. That's what we've got now. This is the thing I want the instantaneous rate of change in. It's a limit as H goes to 0. Of R of what? Well, 30 guitars are being sold here. So that means it's 30 plus H minus R of 30 all over H, okay? Let's figure out what that looks like. So this is equal to the limit as H goes to 0 of negative 4.5 times X squared. In this case, that's going to look like 30 plus H quantity squared plus 1,500X. So that's plus 1,500 times 30 plus H, okay, minus R of 30. So that's going to look like negative 4.5 times 30 squared plus 1,500 times 30. Okay. All goes over H. All right, now we want to distribute things, multiply things out, cancel things out. But we have seen now with some of the examples that there's some arithmetic tricks you can do to see ahead of time when things will start canceling out. So here's an example. One of the steps that I'll need to do up here is distribute this 1,500 in to this 30, and I'll get 1,500 times 30. I don't really care what that equals because I can see pretty much right away it's going to end up canceling out anyways. This minus sign will also get distributed into this set of parentheses, and over here I'll get minus 1,500 times 30. So 1,500 times 30 minus 1,500 times 30, those are just going to end up canceling. Okay, I still need to distribute that 1,500 to that H, which is why I didn't also cross that out. But I can see right away where things are going to cancel. I can kind of see where some other stuff's going to cancel, but I'm not going to jump the gun on that quite yet. So let's write out where we are. Limit as H approaches 0 of negative 4.5. Let's multiply that out. That's going to be 900 plus 60H plus H squared. That's what happens when I square that. We have dealt with this 30 here. It's gone. So now it's just 1,500 times H there. And then this minus sign will distribute in here, and I'm going to get positive actually, negative. So that's positive 4.5 times 30 squared, which is 900. All over H. Here's where I can see something else immediately about to cancel out. Negative 4.5 times 900 is what I'll get when I distribute this to that first term, but I have a positive 4.5 times 900 over here. The nice thing about this is that I don't actually care what 4.5 times 900 is. I don't need to do that in my head. I don't need to punch it into a calculator because I already know those are going to cancel each other out. So who cares, right? I do need to do some multiplication here to see what's going to happen next. So let's do that. We're going to do negative 4.5 times 60. I did not work that out ahead of time, so I'm going to have to do that one in my head, I think. That's going to be 4 times 60 is 240. Half of 60 is 30, so that would be 270. This is negative, let's write the limit down. Limit as h approaches 0, negative 270h. And then here I'm going to get minus 4.5 h squared from this step, plus 1500 h. And then that guy has canceled out. That's gone. I'm seeing some like terms that I can combine. So we have the limit as h goes to 0 of, let's see, 1500 minus 270 would be 1230 h minus 4.5 h squared all over h. And now I can see where things are canceling. These h's cancel, and this h also cancels with one of those. So we get the limit as h goes to 0 of 1230 minus 4.5 h. This is where direct substitution works now. So this is equal to 1230. We need context because it's an application problem. We need units specifically. It's revenue, which is measured in dollars, but specifically it's a rate of change in revenue. So my output is dollars, my input is guitars. $1,230 per guitar. Okay? Now again, remember that is just revenue. So I'm making $1,230 per guitar, but that's not all profit because that will have to subtract away the cost to the company to get these guitars. So this is a retailer, not a manufacturer. That means that this company probably would have bought these guitars at some kind of wholesale price. So a big part of the cost to them is how much they bought the guitar for. They marked it up, they sold it. You can work out profit from there, but we don't have enough information to do that. We have to interpret this answer as well. So this one, based on what we kind of just said, the company makes, makes $1,230 in, in revenue per guitar sold. After selling, how many did we say? 30 guitars? After selling 30 guitars. And again, this is to be treated like an approximation because the amount made per guitar will most likely be changing as we sell more and more of these things. So it's only about $1,230 in revenue per guitar. Let's try to scribble that out. When we sell about 30 guitars. That will change as we sell more and more. Okay? All right. Let's try to knock out a couple more examples. This time I want to find the equation of the line tangent to the graph of y equals x squared minus 1 at x equals 3. At first glance, this might feel exactly like the types of problems we've been doing up until this point. And it will start out that way. But notice the change in the way this was written. It does not say find the slope of the line tangent to the graph. It says find the equation of the line. We do need to find the slope of the line as a part of that equation, but that's not the whole picture. So let's just start with that. Let's find the slope first. The slope of this line, m, is the limit as h goes to 0 of, if I call this function here f of x, it's the limit as h goes to 0 of f of what? 3 is the number we're using here, so 3 plus h minus f of 3 all over h. Okay, so I plug 3 plus h in for the x here. That's going to look like 3 plus h squared minus 1 minus f of 3. Now I plug a 3 in there. Remember, parentheses. 3 squared minus 1. Okay? all over h. Use some of the tricks that we've noticed so far. I have a -1 here, and then I'm going to minus another -1 here. Those are going to cancel. All right, now the limit that I have, limit as h goes to 0, we have to square this. If I square 3 plus h, I get 9 plus 6h plus h squared. And then I have minus 3 squared. That's all that's left here, which is 9, minus 9, all over h. And as you can see, this 9 and this -9 are going to cancel. And then with what's left, there's h's in every term. That's what allows me to do this cancellation right here. Now I'm left with the limit as h goes to 0 of 6 plus h, which is just 6. Now that's not my answer. That's just the slope of that line. To find the equation of the line, we use this. This is called point slope formula, or sorry, point slope form for the equation of a line. You learn about this in algebra. Y minus y1 equals m times x minus x1. The y1 and the x1, those both come from some point that lies on the line itself. And we know that this line is tangent to the graph of this function when x is equal to 3. So what I would want to do is find a point on the line that's shared, or I should say the point on the graph of this function that's shared with this tangent line. I find that by plugging x into the original function itself. So f of 3 is equal to 3 squared minus 1, which is equal to 8. That means that the point 3, 8 is on the graph of both this function and the tangent line. It's the point that they have in common. That's the thing that I'm going to think of as x1 and y1. So taking everything that I found and plugging it into this, I get y minus y1, which is 8, equals m, which is 6. That's what most of our work was going into finding, times x minus x1, which is 3. Okay, I can leave it in this form. I prefer not to. Normally we try to isolate the y, so I could write this as y equals, if I distribute that 6 in, I'll get 6x. 6 minus times -3, that would be -18. And then when I add an 8 to both sides, I'm going to get minus 10. So y is equal to 6x minus 10. That's my final answer for that one. Okay, that's the equation of the tangent line. Notice it's different than just finding the slope. There was more to do. But the slope part took the most of the work that we did in that problem. Okay, last example. Same type of example, but this time we're just using a different function. So I want to find the equation of the line tangent to the graph of y equals root 9 minus x at x equals 4. Same exact process. Start by finding slope. If I'm going to call this function f of x, then I can say that the slope is equal to the limit as h goes to 0 of f of what? Well, it's 4 is what we're using. So 4 plus h minus f of 4 all over what? H. Okay? What does this actually look like for this function? Well, I'm plugging things in for x, so that becomes the square root of 9, so I can turn that into a 9, minus x, so minus 4 plus h. And for the, I don't even know how many times I've said it, but for the whatever time, do not forget those parentheses. You will get it wrong if you forget those parentheses. I guarantee it. Minus, plugging a 4 in, square root of 9 minus 4. All over h. Okay? Simplify things as much as you can. So this is going to become the limit as h goes to 0. I'm going to distribute that minus sign in. So I'm going to get 9 minus 4. That's 5. And then I get a negative h because the minus hits the h also. Here, 9 minus 4 is just 5. So this becomes the square root of 5. Again, all over h. All right, this is an indeterminate form. If I try to plug 0 in for h directly, I get 0 over 0. So I can't do that. I can't just use direct substitution. We have to simplify this, and we have seen how to deal with these types of things. We use conjugates. So that radical there is the indication that I want to multiply by the conjugate of the expression in that numerator. The only difference is I take the minus in between these two radicals, replace it with a plus. I don't change that minus into a plus. Nothing's changing there. But I am changing that middle minus sign into a plus. Make sure we put the same thing in the numerator as in the denominator so that this is an equivalent expression to 1. And then multiply. Remember, the whole point of using a conjugate is because when we multiply these two conjugates together, what I get is this thing squared minus that thing squared. But when squaring either one of them, all that happens is the radical goes away. So I get 5 minus h minus, that radical goes away as well, 5 all over h times this expression, and we don't multiply anything out. We just leave it as is. So 5 minus h minus root 5, like that. Okay? Simplify. Notice the 5 and the negative 5. Those cancel out. I have negative h left on top, but that negative h will cancel with an h down here. And now what's left is the limit as h goes to 0 of negative 1 is what's left up there, over root 5 minus h. And I made a mistake here. That should be a plus. Remember, it came from right there. Plus root 5. Okay? At this point, we are safe to just plug 0 in for h. So I get negative 1 over, that becomes root 5, because h is 0, so that's square root of 5 minus 0, plus another root 5, which I can just write as negative 1 over 2 root 5. Okay? That's it. That's my answer. One thing I do want to point out, oh, actually that's not my answer, is it? That's just the slope. I want the equation of my line. So we'll do that next, but I want to point something out here. In other classes, you may have been taught that if you have a square root or some kind of radical in the denominator of a fraction, you're supposed to rationalize that, which means you find a way to put the radical in the numerator instead of the denominator. We don't really care about that anymore. In calculus, we have no real issue with square roots being in the denominator of a fraction, so I'm not going to ask you to go that extra step and find a way to get rid of that radical. But what we do need to do is find the equation of our line. So remember, our line is a tangent line, and it's tangent to the graph of this guy at x equals 4. So the first thing I should do is find what point this graph shares with its tangent line. That means I need to find f of 4. That would equal the square root of 9 minus 4, which is equal to root 5. Don't plug that into a calculator. Leave it as a radical. It's totally fine to leave that as a radical. The only time I really need you to plug things into a calculator to get decimals is if it's an application problem and we're talking about dollars and cents, right? Because then you would round to the nearest cent. But unless it's something like that, leave it like we're seeing right here. So this means the point 4 root 5 is the shared point between our graph of our function and our tangent line. So this is going to be the x1 and the y1 that we use in point slope form. So now what we have is y minus y1, so y minus root 5, equals our slope, negative 1 over 2 root 5 times x minus x1. So that would be minus 4. Okay? We can leave it in this form, or we can, do some work on it. If I were to multiply this out, I'm going to get y equals, so I'm going to get negative 1 over 2 root 5 x. When I multiply this to here, I'm going to get negative, so this 4 and that 2 will partially cancel out. I'm going to get negative, actually positive, negative times negative is positive, 2 over root 5. And then I'll add that root 5 over, like that. Now, if I did rationalize this, I would be able to kind of combine these two constants into one. It's not super important. I don't care that much about that. I'm going to leave my answer like that. Okay, that's everything for section 2.1. So this was a very long section. We had a whole lot of material to cover, and a part of the reason it was so long is because this process has a lot of steps in it. You know, evaluating the limits of these difference quotients. Fortunately for us, like I said before, we are going to find a way shorter way of finding these instantaneous rates of change. There is going to be some techniques that we can use that takes pretty much all of the work out of this. So look forward to that. That's coming up pretty soon.